These are all of the questions we did in solving exponential equations, just plain exponential equations. We also solved some, I didn't zoom out. We also solved some logarithmic equations. Now these show up a lot in actual real life. These types of equations show up a lot. If you're going to be any sort of scientist, engineer, those sorts of things, these kinds of equations actually do come up. It's not like we'll use it in real life. No. This is actually the types of equations that these scientists or sociologists use to study things. So the first real-world example we're going to have here is all about blood alcohol level. Medical research indicates that the risk of having a car accident increases exponentially as the concentration of alcohol in the blood increases. Okay, we know this, right? We know enough about science. Okay. The risk is modeled by this equation. So the doctors have come up with this equation to represent the risk R associated with higher blood alcohol content, where X is the BAC of a certain person and R, given as a percent, is the risk of having a car accident. The question here says, what blood alcohol concentration corresponds to a 17% risk of a car accident? So in these real-world problems, you're going to have multiple variables in your equations and be given some information in the problem that you need to use. So what are we given in this problem? 17% as a risk. Does that mean they gave me R or did they give me X? R, risk R. See, scientists and mathematicians, we like naming letters, not always with just X and Y because that's boring. We're going to give them a letter that means something. R for risk. Right, R, risk. Okay, great. Now that means what are we trying to solve for? What variable do we not know? X, the BAC. Okay, so let's fill in what we know to this equation. We know that the risk is going to be 17%. It's given as a percent. You don't have to change it to a decimal. Equal to 6 times e to the 12.77x power. We want to solve for that x, which means we are solving an exponential equation. If we think back to the steps we did last class, we need to isolate this exponential expression, which means what do I need to divide both sides by? Well, if I want to get this by itself, e is the base, so I can't divide by the base. 6. We want any coefficient for the base to go away. Now, 17 divided by 6 does not come out to a whole number, so we're not actually going to divide it and put a number down yet. You're just going to leave it as the fraction, because if we round now, we have incorrect data later. If you have to round, don't do it. Leave it as a fraction, leave it as a logarithm, all of that stuff to the very end. Okay, once this base is isolated, this is what we did last time. So the base with the power is isolated. Does anyone remember what we did for both sides? Take the natural log of both sides. So we're going to do the natural log of 17/6, and I'm putting it in parentheses because that fraction, my handwriting is bad enough where I would lose the divide by 6, equal to the natural log of e to the 12.77x. Who notices something nice about this problem? Natural log and the e are going to cancel out because if the base is matched, then that particular thing, since they're inverses, is going to cancel out like addition and subtraction, which means I have the natural log of 17/6 equal to 12.77x. Well, remember, we're still solving for x. We still want that BAC limit. So what am I going to divide both sides by? 12. So we know that the blood alcohol content for the risk of having, or 17% risk of having a car accident is going to be represented by this. At this point, I turn to my calculator. I have done no sort of actual computing yet because all of these numbers I'd have to round. Will you all throw that into your calculator, please? Okay, what'd you get for x? 0.08. So this is the BAC of having a 17% risk of being in a car accident. So yes, that is the legal limit in Texas, 0.08. Let's do another example. We're going to do the second example, or the first example on the back. I really like this one. Has anybody heard of carbon dating? Does anybody know what that is? Carbon dating. This is a science thing. You know how when scientists are like, I don't know, archaeologists, paleontologists, they find really old stuff. They're like, this is old. This is from the, Triceratops age. It's not the right name, but you know what I mean. They're looking at how old it is. They're looking at the carbon dating of the object. Scientists have found constants for different like materials. So if they like find an old bone, they know how quickly bone decays, and so they can measure the carbon left in this bone, use this formula and be like, aha, here's how old it is. Okay? So we're going to use the fact that after 5,715 years, a given amount of carbon-14 will have decayed to half the original amount to answer the following questions. Now, decay and growth in like population is represented by this exponential expression. I've labeled it for you. A here is the final amount, so the growth after a certain year or the decay after a certain time. A naught or A zero in science and math, we call that A naught. It's a zero, but you just say naught. So A naught is the initial amount, so what it started with. Then you have E, that's a constant, that's not a variable, that's the base. To the KT. K is the constant for that object. So like if they were looking at a bone, they'd be like, the constant of bone, we know this, is this, that, or the other. And then T is the time in years that it's been decaying. So we want to find the exponential decay model for carbon-14. When you're finding a model, that means you're writing an equation. So it wants you to fill in all of the variables besides A that you can. Should be having two variables left, A and T, because it's dependent on time. So let's fill in what we know. We know that after 5,715 years, the given amount of carbon will have decayed to half the original amount. How do you represent half? If the original amount was 1, what's half of that? A half, or 0.5. We'll use the decimal. So we have 0.5 is the final amount, or half, equal to the whole. I'm going to use one. I'm using a decimal just because if I put a 1 there, it's confusing. The whole would be a 1. That's the A naught. That's the initial amount, is the whole thing. E to the KT. I don't know the constant for carbon-14. That's what I'm trying to find. But I know the amount of years that we're doing this study is how many years? 5,715 years. Now, T is measured in years. It's not months or minutes. Some other things are measured in months or minutes, but this one is in years. How many variables do I have left here? I only have one variable. E is not a variable. E is a constant, it's a base. I only need to solve for K. Okay? Now, again, if we were doing this like it was an exponential equation, we would want this base to be isolated, which means what do I divide both sides by? 1. That doesn't do anything, so I'm just going to erase the 1. But the 1 was there because it was a whole. Because 0.5 divided by 1 is just 0.5. Okay. What do I do now to both sides? Once the base is isolated. We take the natural log of both sides. So I'm going to do the natural log of 0.5 equal to the natural log of e to the 5715k. Yes, I reordered them. I just like the variables to come second. Personal preference. The e and the natural log cancel out. Very good. So I actually have the natural log of 0.5 equal to 5715k. How do I solve for k? Divide. So I'm going to get natural log of 0.5 divide by 5715 equal to k. At this point, we need to know what k is, but make sure you have your calculator because I'm going to show you a trick in this calculator on how to hang on to that k value for later use. Okay. Now, these k values are usually going to be some sort of decimal that we'd have to round. Actually, they're always going to be some decimal that we'd have to round unless you get really lucky. So we're going to round to the nearest, well, this one's kind of ugly. Usually save 3 decimals, but this one is particularly different. So we have the natural log on top, natural log of 0.5 divided by 5715. A couple things happen when you put this in your calculator. Number 1, this shows up. What does this e mean? Times 10 to the negative 4. So really, when I have this in my calculator, it would give me k is approximately negative 1.2128 e to the negative 4. That's scientific notation telling you to move that decimal 4 spots to the left. So if I unscientific notation this, it is negative 1, 2, 3, 4 That's the value of k. It's very small. And it's very hard to write, correct? Like, I don't actually want to put that number in this equation because the actual equation itself would look like this, the model. A equal to the initial amount, which again was 1, e to the k times t. That's just ugly, right? And if I had to type that back in a calculator, most likely I wouldn't put enough zeros. I know myself. So what we're going to do is right after we get the values for k in these types of problems that you're going to have to use it later, you're going to store the value. Has anybody ever stored a value in this calculator before? How many of you politely ignored this button for your whole life? This one right here. It says STO with the little arrow. That's the store button. So what we're going to do is we're going to store the value of k. Notice when I press it, it says, I'm going to take your answer, which is this, and I'm going to store it as a variable. I like using k, which is, this calculator is too far away from my eyes to see. Is that k? Is it above the parenthesis? It is. Okay. So I'm going to store the answer as k, and when I press enter, it's just going to re-give me the number. That's officially telling me that the calculator has hung on to the number k, or letter k, as this value. Cool. So you can change the letter, but since it's k in the problem, I'm going to use k on my calculator. You could use w if you wanted, but why? So now we have this value stored as k. This is technically the model, but if you have stored it in your calculator as k, you could also write the model like this, because you have k stored in your calculator. As long as you know what k is and you have it listed somewhere else on your paper, then that's the value of the model. That's the equation for carbon-14. Now that we have this model, the amount of carbon-14 left is equal to 1 times e to the kt, where k is stored in our calculator. We can answer part B, which is actually a very interesting question. It says, in 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found by an Arab Bedouin herdsman. Has anybody heard of the Dead Sea Scrolls before? Man, do y'all not watch the Discovery Channel anymore? Basically, they found this pottery, earthenware jars, pottery, for lack of a better term, sealed up with super duper old copies of the Old Testament. So they're calling them the Dead Sea Scrolls because it was found in the Dead Sea and they're scrolls. Y'all know what I'm talking about? They're really, really old documents, and people were like, well, how old are they? But scientists know the formula that we have right here for carbon-14. So they measured them, and the scroll wrappings contained 76% of their original carbon-14. How can we estimate the age of the Dead Sea Scrolls with this information? Okay, I kind of ran out of room here, so I'm going to come over here. If we look and we take the amount, the final amount of carbon-14, which is 76%, this one you do change to a decimal. The only one you don't change to decimal is risk because it's given in a percentage. So 76% is what we know had left, equal to this 1.0 e to the kt power. We now only have the variable t left. Yes, I know k is in my formula, but we know what k is. It's stored in my calculator. So I just need to solve for t. Again, what is 0.76 divided by 1? 0.76. So I'm just going to erase the 1 because it's completely unnecessary, but it's good to see it. And then we take the natural log of both sides. So we're going to do the natural log of 0.76 equal to the natural log of e to the kt power. The natural logs will cancel. I have natural log of 0.76 equal to kt. Remember, k is not a variable. We have a number for k. It's just too ugly to write down, so we stored it in our calculator. We divide both sides by k. I'll go ahead and put this in parentheses because it's kind of confusing. So we have this formula for t. We go back to our calculator, and instead of typing in a rounded version of k, because we lose some details in our answer, we're going to do a fraction, natural log of 0.76 divided by alpha k. I don't have to type in the number anymore. The calculator knows what k is. I've stored it. If I typed it in, there's no way I'd type enough decimals for it to be accurate. When we press enter, it's going to give us that t is approximately 2262, so 2,000, we'll round that up to 3. 2,262-ish years, so 0.7 years, that's fine. But if you answer 2,262 for this question, you're saying the original age of the Dead Sea Scrolls was that. But when we talk about age of items, we don't talk about the years and lapse, we talk about when they were found. So if we took today's, or the date that this was for, so it's found in 1947, and we subtract 2,263 years, it says that the Dead Sea Scrolls were approximately found or written or sealed up in that jar in 315 BC. And then I was curious to see how accurate our model was. I looked at Wikipedia. I know, Wikipedia. But Wikipedia says that the Dead Sea Scrolls were written in 406 to 318 BC. Look at that. Our number that we got is within this boundary. What? Look, that's pretty accurate. Unless Wikipedia is way off, which we understand Wikipedia. It's a good place to start, not a good place to finish. So these formulas, we can write them for exponential growth and decay, and we can use them as long as you store the value of k. Don't round k, because you're going to lose accuracy and get the question incorrect, or round incorrectly later. So that's pretty cool. Something I've heard about in real life is the Dead Sea Scrolls, and it's actually pretty accurate to what Wikipedia said. Again, I know it's Wikipedia. I get it. Okay, we're going to skip the second example, and we're going to go to the first example on the next page. That's about Newton's law of cooling. So this is for all my bakers out there, if there are any of you, or people who are obsessed with the Great British Bake Off. That's me. This question makes a lot of sense for you. Okay, so you know how in the Great British Bake Off, they take a cake out of... Does anybody watch that show? No. Do y'all know what it is? It's basically a cooking show, but it's timed. So the people are like trying to bake this cake, and then they have to decorate it, but they have like 2 hours to do it. So they bake their cake, and all of them immediately go put it in the fridge. Why do they go put it in the fridge? To cool it off. Why would it be better to put it in the fridge than leave it out? Because it cooled down faster. That makes sense to me, right? That's because of this Newton's law of cooling. Newton's law of cooling says that the final temperature of your thing, in this case a cake, is equal to the ambient or room temperature, so like fridge temperature versus room temperature, plus the initial temperature of the cake, or the object, minus the room temperature, times e to the kt, where k is a constant for that item. So like cake is going to have a different cooling off period than brownies because they're different. Or like if you put metal in really hot, I don't know, what's flames, that's what it's called, and then you take it out, it's going to cool differently than cake would. Like every object has a different constant for cooling. And then T up there again. This time T is in minutes, not years, because it doesn't take years for stuff to cool off. It takes minutes. Okay, so a cake is removed from the oven, and it has a temperature of 210 degrees Fahrenheit. We're imagining ourselves on the Great British Bake Off. It is left to cool in a room that has a temperature of 70 degrees Fahrenheit. Total noob, didn't put it in the fridge. After 30 minutes, the temperature of the cake is 140 degrees Fahrenheit. The icing would probably fall off. That's usually what happens when their cake doesn't cool, the like icing doesn't stick, and it's drama. Okay, use the Newton's law of cooling to find the model for the temperature of the cake T after T minutes. Remember, when it asks you to find a model, it wants you to write an equation. So let's fill in what we know. In this formula, it starts with final temperature. What is the final temperature of my cake? 140 degrees. Then I have C, which is the ambient temperature or room temperature. What is the temperature of the room I'm cooking in? 70 degrees Fahrenheit, plus the initial temperature of the cake. What's the initial temperature of the cake? 210 minus, again, that's 70, the room temperature, times e to the kt. Do I know k or do I know t?
Oh, wait, t is 30, right?
T is 30 because it's cooling for 30 minutes. Now, if I fill in everything I knew, what's the only variable you have left? K. Again, we need to find k because it's a constant for cake. If we were doing a different object, it'd have a different k. But since I only have one variable in one equation, I can solve. Let's start simplifying. Now, I know a second ago I said don't do any calculations until the very end, but if it's an easy calculation, it comes out to a whole number, you can do it in your head, just do it. Meaning, if I subtract 70 from both sides, that's going to give me 70 over here. Also, if I reduce this parentheses, 210 minus 70, that's 140. So like, yes, those are easy calculations to do quickly in my head, because they come out to nice, pretty numbers. If it was a decimal or a fraction, or if I had to round, don't actually do the computation yet. Well, this is just an exponential equation we need to solve. We're going to go ahead and divide by 140 on both sides. So we have 70 divided by 140. Yes, I know that's a half, but if you don't notice it, I'm going to leave it as 70 divided by 140 for now. We take the natural log of both sides. What happens there? Yay, they cancel out, which means I have only 30k left. Now, just because I'm running out of space, I'm just going to Frankenstein this together. How do you get k by itself? Divide by 30, so I'm going to do that on both sides. Great, I have a value for k. And I can go to my calculator. Now this is going to give you, again, some decimal that we're going to want to store because we see it's a multi-part question. We're going to need to use k. This k is a lot prettier than the k we had before, if you guys would help me out. We're going to round k to the nearest 3 decimals, to the nearest thousandth, to write it down, but we're going to store the whole thing in our calculator. I guess I should do this too. Okay, so we have this approximate value for k, negative 0.023, which again is a nice rounding we can write down, but we want to store it in our calculator for use later. So immediately after typing it, you press store as k. Yes, I know we already stored something as k, but this will overwrite that. So now if I put in k, it's going to give me this value instead of the value we used on the problem before this. So your calculator hangs on to the value you tell it. Cool. So if we were writing the actual model here, it would be the temperature of the cake, the final temperature T, equal to room temperature, which is 70, minus, we can go ahead and simplify that to 140 because 210 minus 140 is, 210 minus 70 is 140, times e to the kt. We can leave it as k because we know we rounded the k value to approximately 0.023. We have that written on our paper somewhere else, so we can leave it as k. If k were prettier, we could plug it in, but it's rounded. So that's the model. It's the equation. Part B asks, what is the temperature of the cake after 40 minutes? If they gave me 40 minutes, the only 2 variables I have left are big T and little t. Did they give me big T or little t? Little t. They gave me a time. They gave me the input of 40 minutes. So really what I'm trying to figure out here is what is t when you take 70 minus 140 e to the k times 40. There are no variables left except for t, because k is not a variable anymore. We have a value for it. This is just a plug and chug. If you let that cake sit out for 40 minutes on the counter, how hot would it be? So we ask our calculator. Oh, I lost my calculator. Here it is. We would do 70 minus 140 times e to the, I need e to the, that button's right here. Above the natural log, there's a button that's literally e to a power. So you press second and then that button.
You said 7.
Oh, I'll go fix it. Thank you. And then up in the exponent, I want the number k because I have it stored as a value. And then I want the number 40. When you get it written in your calculator, just like you have it written on your paper, you press enter, and it's going to tell you, okay, so my bad. I read the equation wrong. This should be a whole plus sign. I was like, why did that get so cool so quickly? That's not how it works. It's not going to get to 14 degrees Fahrenheit that quickly. Okay, so I need to retype it. I'm going to press second enter. It gives me the whole thing again, and I'm just going to go over the negative sign. Look, I did this on purpose to show you how to use your calculator. And we get 125.55. So the final temperature of this cake after it sits out for 20 minutes is still over 100 degrees Fahrenheit. Still very hot cake. If they were on the Great British Bake Off, you'd have been like, nope, you didn't put it in the freezer. Like, your icing's definitely melting off of that. Okay, then we have a part C on this question. Part C says, when will the temperature of the cake be 90 degrees Fahrenheit? So did they give me big T or little t? Big T, that's a final temperature. Still sounds like 90 degrees Fahrenheit. My icing's going to slide off. Again, didn't put it in the freezer. Total noob move on Great British Bake Off. So we have 90 equal to 70 plus, change my plus signs to the correct thing, 140e to the kt. Remember, k is a constant we already have. T is the only variable. So we're just resolving now for t. Can I leave you guys to find t? You're solving an exponential equation for the time it takes for this cake to cool off to 90 degrees Fahrenheit. Okay, so if we were solving this one, you'd subtract 70 from both sides. You'd have 20 equal to 140 e to the kt. Divide by 140, which does give you a fraction, 1/7, but you can leave it as this if you don't see that. We take the natural log of both sides. I'm going to have to scoot over. We take the natural log of both sides. It would be the natural log of 20 divided by 140 equal to the natural log e to the kt. We celebrate a little because the e's and natural log cancels. So natural log of 20 divided by 140 equal to kt. But if I want t, I'm going to divide both sides by k. I just did that one step to save space. When we do that in our calculator, you have to press this k button, alpha k, because you've stored k value. We should get a time. So if we let this cake cool on the counter, it's still 90 degrees. How long have we waited? 84.22 minutes. That's a long time. If you were on the Great British Bake Off, they usually only get 90 minutes to 2 hours to bake something. They just let that cake sit out for an hour and 24 minutes. They were going to lose. So you got to understand Newton's law of cooling to be on the Great British Bake Off. That's when you would use the freezer to cool it off faster because the ambient temperature would be more. Yes, ma'am. Now, the only other example we're going to do today, I know I keep skipping around, is this last example, or the top example on the last page. It's the last two examples here are actually very interesting. We just lived through a pandemic, I guess we're still living through a pandemic, so the spread of the flu, that's an interesting example. Also rumors, very interesting example. But we're going to do this one up here about sound intensity. So sound intensity is all about how loudly you, me, humans hear sounds. Every being has a different sound intensity that they register. So like, you know how dogs can like hear things people can't hear? It's because their ears hear a different intensity than ours do. Now this is going to be represented by this formula called beta. That's the Greek letter beta. Is equal to 10 times the log of I over I naught, where I is the sound intensity from this table. We've measured the sound intensities. And I naught is 10 to the negative 12. It's the threshold of human hearing. So that's how much we can hear at different sound intensities. So if we wanted to figure out the decibels for these different things, which, fun fact, does anyone know why it's called decibels when you talk about how loud something is? Did you even know that's how you measure things on how loud they are? Yeah. Decibels. So if you think about like the origination, the guy who invented like telephone or started the telephone, does anybody know his name? Alexander Graham Bell. So he named the first unit of sound after himself, a little conceited, but they were called bells. But then when we got better at the math behind it and the science behind it, we're like, we need a smaller unit of measurement than a bell. So we made it a decibel, which is a tenth of a bell. Fun fact. I didn't know that till I was Googling this earlier. I thought that was pretty cool, except how conceited to name it after yourself. I guess I'd love to call something a quig, you know. I name my Quigbucks, so I guess it's the same thing. Okay, if we want to compute the decibels that humans hear for a soft whisper, all we would do is plug in what we know. We don't know beta because that's the sound intensity, but we know that the formula has a 10 times a log of I, which from this table, the sound intensity of a soft whisper is 10 to the negative 11ths. Over I naught, which is always 10 to the negative 12 for humans. That's the number from up here. It's basically a constant, and it changed, like the K changed per object for the carbon-14 or for the cake. The sound intensity I naught is going to change for humans to dogs to cats. Okay. Now that is all things I can type in my calculator, which is what we're going to do. So sometimes it's, again, just kind of like a plug and chug thing. We want to know what 10 times the log of the fraction 10 to the negative 11th divide by 10 to the negative 12th, close parentheses. I know you don't technically need to close those parentheses, but I come from the era of parentheses. We had to close them, so I'm used to it. When we press enter, we get 10. So the sound intensity that humans hear, a soft whisper, is 10 decibels. It makes sense. It's pretty soft, right? Okay, now what about city traffic? How loud is city traffic to us? Well, that's going to be beta equal to 10 times the log of this times city traffic based on my table is 10 to the negative 5 over 10 to the negative 12. Again, to save time in the calculator, it's really why I'm showing you this example, I want to rewrite this. So I press second entry. It's going to retype the whole thing because the only thing I changed was this value up here. It's not negative 11 anymore, it's negative 5. So I can type it much faster if I just edit. Which means I pressed delete. Because there was 2 digits, I only wanted 1. You delete 1, then overtype the other one. Up at the top, it says DEL. So a city traffic, we hear at 70 decibels. So it's 7 times as loud as a soft whisper. Now, what about a jet? Obviously, a jet, it's going to be very loud to humans, right? That's why the guys who do the you know what I'm talking about with my hands? They are always wearing earmuffs because the sound intensity of a jet at takeoff, way too loud. So let's figure out how loud it is. So beta is going to be equal to 10 times the log of, this time 10 to the third power over 10 to the negative 12. Again, I just retype what I have in my calculator since I already typed it. Second enter for entry. I want to get rid of the negative up there, so I'm going to go over the negative, press delete, and I'm going to change that to a 3. It just allows me to type it faster. So we would hear a jet take off at 150 decibels. That is also approximately the level of music you guys play your music at in your AirPods sometimes. I'm just kidding. But actually, though, you're going to bust your eardrums out. Coming from experience, because I have bad hearing now, and I'm too young to have bad hearing. I did not believe my mom when she said it, and now I can't hear anything. Okay. That's the only examples we're going to do out loud today. Obviously, the rest of the examples are on the notes online if you're curious about some of them. Like I said, some of them are really interesting, like the flu one and the rumors one, actually pretty interesting. But I would rather give you time to work and study.